Okay, you see my screen, and you can also hear me? You hear me? Okay, perfect. So efficient mass data replication via OData in CAP. What can you expect in the next 20 minutes? So we first have a look at the mass data upload side. I will show you OData batch requests and how you can use them already in older CAP versions for mass data upload. And then we show you a more efficient approach with the entity collection delta updates that are available with OData v4 in CAP Java. And they're using native DB upserts in CDSQL. And you can also use these in deep upserts and updates, and I'll also show you that. And the second part, Adrian will talk about the mass data download side with reliable pagination. In between, I will show demos. So we run here on a CAP Java stack with the bookshop model. I guess this is well known. So we have books with the title, stock, and associations to authors. We have authors with the name and many books, and there are also orders with many items that can point to books. So that's the demo application. Let's first have a look into OData batch requests. For OData batch requests, and there you basically can group many individual requests into a single post request. So this is pretty powerful. However, the requests inside of the batch, they are handled individually. And that also means that all the CAP handlers internally have to run for all the requests inside of the batch. And this is a little bit inefficient for mass data uploads. But let's have a look into an example here. So you see here such an OData batch request. It goes to the service endpoint with $batch. It's a mixed multi-part, and you define a batch boundary. And inside of that boundary, you then can combine multiple other requests. So for instance, we want to delete one of the books, then you have another request that does a patch on the books, which is basically an upsert, and later another patch for a different book here. So this is kind of OData batch request that is available also with older CAP versions. So now if we execute this request against the CAP Java runtime, we see there are already a couple of statements executed. So we have here the delete for the first content, the first request, and then for the two patches, each we have the runtime tries to do an update first. The update does not hit anything, and therefore there is a fallback to an insert. So already for this small batch, there are really a couple of statements executed in the runtime. Now let's try to use this for mass data upload. Let's start here small. This is a batch request with 1,000 patches, so 1,000 entries into books. And now if you run that, we see there are really a lot of statements executed here in the runtime. And all these patches basically result in tried updates that don't match anything, and then a fallback to an insert. This is still here kind of not too slow because it runs on an H2 in-memory database on the same machine, but it would look differently for a productive environment where the database is not here on my laptop in the same process. So we definitely want to improve on that. And luckily, since end of last year, we have a new tool in our toolbox. So we introduced support for native DB upserts in CDSQL. So DB upsert is basically an update or insert with a single statement on the database. So it's more efficiently than just first trying to update and then falling back to an insert. And this now we added support in CAP Java and also in Node.js. So how does this look like? You have the new upsert statement. You define the entity you want to upsert in. And then you can provide multiple upsert entries. the entries are identified by their key values, and then you provide the upsert data. In CapJava, you also can combine multiple entries with different values for elements. So for instance, the first two entries, they would just upsert the title and the stock, and the others, the title and the author ID. So the structure does not have to be the same. And then in the Java runtime, we automatically group these and efficiently execute that in batches. For instance, for HANA, this would result in 2 upsert statements with batches for 101, 102, and there's another statement for book 201 and 202. And this not only works for HANA, but also on SQLite and Postgres, on also in CapJava on H2. One thing that you have to keep in mind when working with Upserts is that the improved efficiency comes with a small price. So we cannot distinguish anymore in the Cap runtime between update and insert. And that means some features we would automatically do on insert don't work here for Upsert anymore, like the generation of your UID key values or default values, or also the handling of CDS on insert values. And also some of the generic services like audit logging that require the distinction between insert and update also don't work out of the box. However, for things like mass data upload, this usually is not an issue. And with the native Upsert in the toolbox, we then in CapJava implemented support for entity collection delta updates in OData v4. So how does this look like? There you have a single patch request, and you define in the context that this is a delta update or delta upload with the context delta, and then you just provide the upsert data in the values attribute here. So everything that you see here is then natively upserted. And additionally, you also have the possibility to delete some entries. This is done by also adding the entries here with their values and having this removed annotation with an optional reason. And this would then trigger deletes on these books. So now let's have a look at an example. So for the batch with the 1000 entries, we also have a patch request here. Also upserting 1000 entries with the delta request. So this is a patch on books. Let's also have a look here at the logs. And now if we execute this request, you see this returns in 80 milliseconds instead of over a second. And on the database, you see there are only 2 upserts. So in H2, the upsert is basically merged into, and each of them in a batch upserting 500 rows, which is way more efficient. And since this works much faster, we can also just do this for 10,000 rows. So let's do this again with 10,000 entries. And we see here in the database statements take around 60 milliseconds with 5,000 rows each. So just much faster than the OData batch request we have before. Okay, now the only thing, if you want to use that to enable this in your application is, so you go in your service definition, and for the entity, you want to enable these delta uploads. You just annotate this with capabilities, update restriction, delta update supported. And then the Cap runtime basically supports these delta upserts for this endpoint. Now you know about these delta updates. You might wonder if this also works for deep updates and deep upserts, and there the answer is yes. So you also can do this in deep scenarios. So let's first have a look into the deep update, deep upsert, as it was supported already since 2020. So here we have the full set payload. We want to upsert an entity orders, update the shipping, the status to shipping, and then we provide data for all the items. And here items is provided as full set. That means so everything in the set here is upserted, and everything that is not in the set will be automatically deleted by the CAP runtime. And in order to delete it, we first have to do a select statement, select all the items, and compare the state that you sent with the state on the database, and then execute deletes. And this is quite a heavy operation. And also you are forced to include also all the entries here that you don't want to change, but still should be in the set. Now, we also support the delta semantics here that I showed you before. And the only thing you have to do is to add to suffix the items in OData with an add delta. And then you have delta semantics for the set, as in the delta upload scenario. That means everything in there is upserted. You have the possibility to also delete by explicitly annotating elements with it removed. And everything else that is not mentioned is just not touched. And therefore, the CAP runtime also does not need to execute a select and compare the state. So let's also have a quick look here at an example. So here you see a deep update with the delta. So first what we do is set up the stage. So we do a deep insert with an order that has 6 items. And then we do a deep delta update. So we do a patch on this order. And in here, the items, they are just provided as a delta. And we want to delete here item 1, item 3 and 4. So we annotate it with removed. And the other items, they are just upserted. And you see they have also different elements. So for the first 2, we quantity, and the last 2 also have the book ID set. So now if we execute this request here, we also see the statements on the database, and also see here using delete 2 merge statements, which are the upserts, and finally updating the root entity and setting the updated at timestamp. So that was basically the part on the mass data upload side, and Adrian will now talk about the mass data download and reliable pagination.
So, thanks, Matthias. So we also have news in the area of mass data download. Assuming a client sends a query which requests a very large set of data because it wants to replicate the data from the server to the client, then of course the server can't just answer this request because handling this very large set of data might exceed the memory limits of the server, and therefore the server automatically limits the amount of data returned. This is what we call implicit server-side pagination. But the client, of course, is not lost because the response contains a next link. And if the client then executes the query specified in the next link, it just gets the next page, which will again be limited by the server. And so in this way, you can just download page by page a very large data set. To allow for this, of course, a precondition is that the server applies stable sorting. So in this request here, no order by is specified explicitly by the client. And in this case, we implicitly and then sort by the ID of or by the keys of the books entity. this scenario is not only useful for downloading huge amounts of data, but also for like infinite scrolling scenarios, for example, where the user can well, scroll down on a very large page of data, and the data is then just well, loaded chunk by chunk by the UI. But it's also limited to forward scrolling only scenarios, because you can't just randomly access a particular page of the data. For this you would have to specify $top and $skip in the OData request. So our current implementation is offset based, meaning that the skip token, which you have just seen here on this previous page, just contains the number of rows to be skipped. And so essentially then the skip token so far just translates to an offset clause in the SQL statement. But this issue, this implementation has two pretty prominent issues. One is a functional issue, because it can lead to the observation of lost or duplicate rows in the client. Maybe I try to explain it in words. Assuming you have already downloaded a few pages of data, and then someone else deletes data on a page which you have already downloaded, then all the data moves up by one row. And this has then the effect, if you download the next page, well, the row you were just about to read has moved up to a page which you have already read, and then you never get to see this row. So in this situation, you lose rows. And in the other situation, if someone inserts data on a page which you have already read, all rows move down by one row, and this can lead to the effect that one row which you have already read, you will read again. So this is what we call an unreliable result. I don't know whether this is a very technical term. To avoid this, we implemented reliable pagination. And what we do there essentially is that we do not have a numeric skip token, but instead a skip token. Yeah. Instead, the skip token just captures the values of the elements by which you sort of the last row of data which you have read. And then instead of using the offset here, we just add a condition to the where clause, which allows you to navigate directly to the page which contains all values which you have not yet read. And the advantage, obviously, is that we avoid duplicate rows. There's also a performance advantage, because if we use the offset here, the database needs to scan over all rows if the offset is very large until it finds, let's say, the 1 millionth row which you have not yet read. On the other hand, in contrast, if you use the comparison predicate in the select, the database can use an index to, well, directly seek to the page, and it has a, well, time complexity then of n log n, which is very much faster. Maybe, I guess I have time to show you one request. So if I execute this request, I order by title, then we see here I get a next link with a skip token. If I copy the skip token, paste it here, execute this request. Maybe I pasted it wrongly. Don't want to fix this, but maybe what I just wanted to show you, the content here of the skip token is essentially well, a UU encoded JSON, roughly looking like this. This is not a spec. Content might change, but it, well, contains the values here for the key is the title, which I explicitly specified here in the order by clause. And then I also need to implicitly sort by ID to make the result, to enforce a stable ordering from the result. And these here are then the two values for the last row. Okay, and maybe I give it, guess time is up, right? I need to summarize. Okay, then let's come to a conclusion. So what did we see here? Key takeaways. So Matthias showed you that we have now in our toolbox a new tool, which is DB native upsert statements in the particular dialect of the various databases which we support. And although this is very efficient and much faster than executing individual insert and update statements, it comes at the price that we can't distinguish between insert and update any longer, and therefore our handlers are not called. It is available in a bulk flavor, in a deep flavor. You can use it also in OData to execute patches against the entity collection. And the last thing which we showed is that on the download side for mass data replication, we now support a feature which we are calling reliable pagination, which uses values of the last rows of data in the skip token, and this avoids the phenomena of lost or duplicate rows in the download, and also has a more stable performance as opposed to the numeric skip token.
Okay, thank you, Matthias and Adrian.